Okay, so welcome everybody once more to the official IAU G2 online conference series. As usual, this is about massive stars, and today is my real pleasure to introduce our new speaker, Varsha Ramachandran, who is presently a postdoctoral researcher at the Astronomischen Röntgen Institute. I hope I pronounced properly, at the University of Heidelberg. She started her career as an astrophysicist at the Indian Institute of Space Science and Technology, where she obtained her master's degree in 2015. And after that, she moved to the University of Potsdam, where under the supervision of Walt Rainer Hamann, started to conduct several quantitative spectroscopic studies of OV stars in the Magellanic Clouds. And this allowed her to be awarded a PhD degree in 2019. The title of her thesis was Massive Star Evolution, Star Formation and Feedback at Low Metallicity, and this was a research line which she has been developing further since then, first as postdoc at the University of Potsdam, and afterwards since 2021 as part of the team led by Andreas Sander in Heidelberg. So everything is ready to start enjoying together with what Varsha will be telling us about the importance of studying massive stars in low metallicity environments and what we've been learning about their physical properties and their evolution, the context of single and binary evolution in the last years. So whenever you want, thank you very much for accepting our invitation, Varsha, and whenever you want, the floor is yours.
Thank you very much, Sergio, for the introduction and also for inviting me to give this talk. So I'll be talking about, as you see in the title, metal-poor massive stars, what we learned from spectroscopy. And before that, I will try to give you a very brief and very basic introduction about what we mean by metal-poor massive stars and what is really a metal-poor. So let's start with some very basic definitions for metallicity. So all we know, like in astrophysical context, metallicity means abundance of all elements heavier than hydrogen and helium. And of course, we have precise measurements for abundance of metals in sun, in our own sun. And this is typically used as a reference point. And stars with low metal content than sun is typically we call as a low metallicity star or metal poor star. But in reality, in different astrophysical research contexts, metallicity can have a very different meaning. So I will try to give a few examples for that. For example, when you deal with nebula metallicity, for instance. So people are measuring metallicity from the emission lines and ionized gas spectra to get chemical composition of the ISM. And typically people measure CNO and a few other alpha elements. And especially in extragalactic studies, oxygen abundance is often of the nebula is often used as a proxy for metallicity in such research. On the other hand, people who study stars and try to get chemical abundance from the stellar spectra using absorption lines, they typically use iron abundance as a proxy for overall metallicity. And sometimes if one cannot really deduce iron composition, people often measure abundance of light elements such as CNO and other alpha elements, and average of these are also sometimes used as a proxy for metallicity. So metallicity can be a term can be used for basically different abundances. So saying that, we can go into the definitions for metal poor stars. So metal poor stars is often a term used in the context of low mass stars because low mass stars can have a very long lifetime, sometimes as long as the the age of the universe. So we can see this very like fossil stars which had formed very early in the universe, and which shows very extremely low iron content in their spectra. So in low mass star context, you can classify them in very different categories based on the scaling of iron abundances in those stars. But on the other hand, massive stars are very important, especially they are the drivers of the cosmic evolution. So in terms of their stellar winds, ionizing photons, and finally, as a supernova explosion, they have a strong impact on the surroundings in terms of chemical evolution or like the whole feedback of the galaxies. Even after the supernova explosion, they create this compact objects which will eventually merge and form gravitational wave source as we observe nowadays. So in that context, understanding massive stars very early in the universe, or basically metal poor massive stars, is extremely important. But the problem is they have very short lifetimes, not like the low mass stars. So we cannot really directly observe such very ancient stars in our own galaxy. And the other way is to directly observe stellar populations in very high redshift galaxies, which is also kind of impossible because one cannot really resolve individual stars at that high redshift. So the only possible way to really look at or observe metal poor massive stars is to go regions where there is minimal past star formation, such as dwarf galaxies. So because of low star formation in the past, the ISM basically preserve primordial composition. So we can directly observe metal poor massive stars, which kind of reflects population very early universe. So then it comes another important question is this metal poor massive stars we observe in the nearby dwarf galaxies really have a chemical composition or metallicity compared to high redshift galaxies? We all know about the cosmic evolution of metallicity. So the first stars, or the POP3 stars, were only composed of hydrogen and helium. And later, after generations of star formation, the metal in the ISM start to enrich. So the recent JWST studies of high redshift galaxies gives a better view on how metal rich, or like what is the metallicity of these galaxies in such high redshift universe. So I'm showing here some of the plots from very recent studies where they combined analysis of galaxies at high redshift up to 10 redshift of 10. And they basically measure the oxygen abundance in the gas phase of these galaxies. And you can see, compared to the average metallicity of galaxies at redshift 0 is shown in the black line also here. And this compared with the high redshift galaxy metallicities, which are much lower. So you can see this goes towards up to 2 or 3% solar. So in order to basically understand this early universe or stellar population at these high redshift galaxies, we basically need to study the metallicity range between at least 20% or below. So something close to 2% solar. Then the question is, do we really observe such low metal content stars in our nearby dwarf galaxies? So here I'm showing few plots from the literature. So in the left, I'm showing again oxygen abundance for different dwarf galaxies. And the red box is actually same as the metallicity range we see in the high-redshift galaxies. So that actually means it's very interesting that we can actually observe massive stars in these dwarf galaxies and directly compare it with the high-redshift universe. And some of these dwarf galaxies also have constraints on the iron abundance, not just the oxygen abundance. So this is also shown in this figure in the right side. So including SMC and some of the nearby dwarf galaxies show really low iron content and oxygen content, and it's really useful for studying such metal-poor massive stars. Another important aspect I want to show and highlight is when we basically study metal-poor stars within the range of roughly 50% to 3% of solar. We cannot directly compare it with the classifications we have in the low mass star context. So in low mass star context, there are so many classifications for metal-poor massive stars based on the iron content. We are dealing with a completely different mass metallicity or low metallicity range for the massive stars. So probably we need to come up with different classifications schemes to refer different metal poor regimes. So saying that, I will move on to the quantitative spectroscopy of metal poor massive stars. So quantitative spectroscopy is a very powerful tool to understand properties of massive stars or in general stars. So here we create synthetic spectra based on non-LT atmosphere models, and which are often defined by stellar parameters, wind parameters, and chemical composition. So by varying these different parameters, we can create synthetic spectra in SED and then try to compare it with the observed multivalent spectroscopic data. And using a different kind of fitting processes, we can finally get a matching fit between, or the best fit between the observed spectra and the synthetic atmosphere model. And this will give you the properties of stars. So these kind of spectroscopic studies have been done for many OB stars, especially in the Magellanic Clouds, because they are the closest galaxies where we can observe low metallicity massive stars. For example, large Magellanic Cloud has a metallicity of half of solar, and small Magellanic Cloud has a metallicity of around 1/5. And they are so close to the Milky Way. So with only a distance of 50 to 60 kiloparsec, we can resolve individual massive stars and study a large number of stars with spectroscopic data. So this has been done in the past few decades. I'm quoting some of the large spectroscopic studies here. And most of them were focusing on individual giant star forming regions or individual massive star clusters. And recently, there has been large spectroscopy campaigns focusing on the UV spectroscopy of massive stars in the Magellanic Clouds called Ulysses, also combined with the optical X-ray spectra. So this has been taken for stars across the both galaxies, not in individual star-forming regions. So this gives a better view on the stellar wind properties of massive stars because of the UV capabilities. And there is also another very recent campaign called Binarity at Low Metallicity Bloom, which covers 25 epochs of spectroscopy of almost thousands of OB stars in the SMC. This will give a more understanding on the binaries binary properties at low metallicity. So I will include some of the preliminary results from these studies in my talk. Saying that, so far, although we have a good understanding and good spectroscopic studies in LMC and SMC, we still are limited to a metallicity of 0.2 or like 20% solar. So that's kind of a empirical constraint or anchor we have for our understanding of low metallicity massive stars. But this is not really enough. When you remember the diagram I showed, 20% metallicity is kind of on the border, and we need to really go down in metallicity to better understand this high-redshift population or very early massive stars. So there has been many efforts in the past decades to observe sub-SMC metallicity stars in dwarf galaxies especially. So I'm showing here, listed here, some of the recent studies, and in the table you can see different galaxies, their corresponding distances and metallicity in terms of iron provided by stellar spectroscopic analysis, mainly from cool supergiant studies, and also the nebula oxygen abundance. So looking at the table, you can clearly see most of these dwarf galaxies are, although they are nearby dwarf galaxies, they are as far as like almost a megaparsec scale. So it is still very hard to really get very good resolution and very good quality spectra and avoid composite spectra and so on. So there are certain challenges in observing OB stars in this distance metal poor galaxies, but these are the only way to basically understand a large number of OB star properties, metal poor OB star properties. But recently we find a very good laboratory of metal poor massive stars in the nearby range, which is called the Magellanic Bridge. And this has only a distance of 55 kiloparsec, basically sitting in between LMC and SMC. And it also offers a metallicity range, which is similar to what other dwarf galaxies offer. And the interesting thing is, since these are very close by region, you can have very high resolution spectroscopy with high signal to noise, and you can basically precisely measure chemical composition of stars at such low metallicity. So here I'm showing a comparison of some of the spectra taken for Sexton A O star and Leo P O star. And these small red rectangles basically is the same range, wavelength range, and you can see how clearly in bridge stars one can observe different metal lines, for instance. So Magellanic Bridge is although it's not really a galaxy, it's a tidal interacting zone between LMC and SMC. It offers a unique laboratory for low metallicity massive stars, and we used a high resolution VLT flame spectroscopy and found many B stars and B stars in the region, but we recently discovered 3 O stars among them and studied them in detail. So I will talk more about these 3 O stars in the bridge, which has very low metallicity. So one of them, these are called MbO2 and MbO3, and we found that these are very slow rotating stars at low metallicity. So you can see in this, the spectra shown here in the right side, which shows the carbon 3 absorption lines. and they are very narrow, and I'm trying to compare it with models in the red dashed line. And you can see they have very small rotation. So even without assuming any V sin I or Vmax, you can basically try to account for the broadening just with the microturbulence. So both stars have rotation much lower than 10 kilometers per second. And of course, it's very uncommon at low metallicity, but it's a very ideal for estimating chemical composition. Why it's so uncommon? Because typically massive stars in general rotate faster at low metallicity. So here I'm showing a rotation velocity distribution for OB stars in LMC and SMC and galaxy from multiple surveys. And you can see that the main peak of the distribution basically correlated with the metallicity. So as you go down towards low metallicity, stars are often rotates really faster. But again, this is limited to SMC. We don't have such large scale surveys at low metallicity. But even then, I try to plot a similar distribution from limited sample available from these low metallicity galaxies. And this is also kind of in agreement with what we see in SMC. So all observations suggest that massive stars in general rotate really faster at low metallicity. But this is actually a bad news when you try to measure the chemical composition and study them in detail. But fortunately, these bridge stars have extremely low V sin I. We were able to precisely measure the abundances. So in this plot, I'm showing two different stars and their corresponding metal lines. And you can see one of them has a very weak or diluted metal lines due to low chemical abundances. So for example, for MbO3 star, we measured almost 8% solar chemical composition, or like mean abundance of light elements. On the other hand, the star MbO2 has only 4% of metal abundance. And the interesting thing is this star also have an extremely low nitrogen content, which is never seen before in nearby galaxies or in nearby stars. Another fascinating thing is both these stars are sitting in a very close location. So the spatial distance is only 15 parsec. Still, these show completely different chemical composition. Another star we studied in this work was MbO1, and we found out that the star indeed has almost LMC-like chemical composition, which is much higher than the other two. But anyway, we only studied the optical spectra, and we only have the light elemental abundance. To understand the actual metallicity of these stars, one would need iron. One we need to constrain the iron abundance. But to constrain iron abundances in O stars, hot O stars, is very tricky and complex because we do not observe usually iron lines in the optical, and one has to get UV spectroscopy, UV spectra for that. So in UV, you can basically see not just few lines, but like a forest of iron lines with different ionization dominates in the different parts of the UV. So typically for O stars, you have to basically look at the FUV range, which has more prominent iron 5 and iron 4 lines, which are important to deduce iron abundance of O stars. So in this spectral plot, I'm showing a comparison of how different iron abundance can affect the this iron forest features, for example. So I'm showing all of them are a very late type or dwarfs, and in the same spectral range, and all have narrow or like narrow lines of very low rotation. So the first one is the LMC star with approximately 50% solar, and the SMC star, and then there is this bridge star. So you can clearly see the iron lines are extremely weak as we go down to the bridge stars. But again, one cannot naively get an idea about the iron content just by looking at the iron forest. For instance, the orange spectra is again an O-dwarf star, but in the SMC also show very weak lines, but this is just due to the rotation. So that means iron abundance estimation from the UV forest is extremely complex and highly dependent on the broadening parameters like Varsha and microturbulence. So one has to use some detailed techniques to measure iron abundance. So we follow with this, for these stars, we follow with the HST UV spectroscopy to basically understand the iron abundance and how iron to alpha to iron ratios changes in the bridge, and also to understand the stellar winds at low metallicity. So our PhD student Eliza Schuster, she will be working on these spectroscopic analysis of the UV spectroscopic analysis of bridge stars. And she started working on deriving the precise iron abundance from the UV forest line. So we fixed the stellar parameters from the optical analysis and only changed the iron abundance to fit the UV iron forest lines. And she used a Bayesian analysis for that. So for example, here, this is a final best fit model for a fixed microturbulent velocity, which is derived from the optical. And you can see using this Bayesian sampling, you can get a precise value for the best fit iron abundance for this both bridge stars. And one can see one star has around 10% iron abundance compared to solar, and another star has very low, as low as 3% iron abundance. But we only did this for one particular microturbulence velocity, but this can have quite an impact on the derived iron abundances. So in this figure, I'm showing how microturbulent affects the derived iron abundances. So the blue corresponds to the star MBO2, and the orange lines points corresponds to the star MBO3. And you can see in both cases, when you vary microturbulence, this can affect a factor of 2 on the derived iron abundance values. So, but one can estimate the accurate microturbulent velocities from the shape of the metal line profiles. So she tried to get a better estimate on the microturbulent velocities, and here I am showing the chi-square values for how good the fits of the metal lines are for different microturbulent velocities. So combining this different posterior distribution for a range of microturbulent velocities, we found a final abundance, iron abundance values with the much more precise uncertainty ranges. And finally, we can say that one of the star has approximately 11% iron, and another star has about extremely low iron composition, around 3.6%. And the very interesting thing is the stars we measured chemical composition from the optical spectra. MBO3 was showing much higher mean value of abundance of light elements compared to the very low iron abundance measured from the UV spectrum. So we derived the overall metallicity based on all this chemical composition that we measured. And MBO2 has around 4% solar overall metallicity, and MBO3 has around 8% solar. And in the right side plot, I'm showing for 3 different Bridge stars how the chemical composition of the chemical abundance of different elements varies. So it's not a very linear scale, or like all the elements are not scaled in the same way. So for example, the star MBO1 has a very high metallicity, something like a LMC star. And in green, I'm showing the star MBO3, which has extremely low iron content, but has much higher abundance of other elements. And the star MBO2 has 10% iron, but other elements are extremely depleted. And especially when you look at the oxygen abundance and iron abundance, is actually going in the opposite direction. So the star which has high iron has an extremely low oxygen. So this suggests that one cannot naively assume if you get a higher oxygen abundance or lower oxygen abundance, iron would follow the same trend. This is a bit, one has to be really cautious assuming such abundance of metallicity assumptions. And we also did try to understand how alpha to iron changes for these 2 stars. So for example, the star with extremely low iron content shows some signs of alpha enhancement. So it has a high oxygen, silicon, and magnesium relative to iron. On the other hand, the other star, which has a relatively higher iron, doesn't show such alpha enhancement trend. So even these 2 close, very nearby stars shows very distinct alpha to iron ratios in the bridge. Combining with other previous observations of B stars, but these are basically from LTE analysis, and also the ISM abundance of some parts of the bridge are also plotted here together with our chemical composition of bridge stars. And you can see this whole region is has a very it's very chemically homogeneous and has a range of metal compositions or metallicity. So you can see this varies between roughly LMC like 50% towards extremely low as 3%. So bridge actually offers quite a range of metallicity to study metal poor stars. So we know to better understand more, to study more metal poor stars, we follow up with high resolution UV and optical spectroscopy across the bridge. This will give a better handling on how diverse is the chemical composition of the bridge ISM, as well as to study properties of massive stars at low metallicity in the nearby universe. So I will come to the stellar wind. What is our understanding on stellar winds at low metallicity? So this is mostly based on LMC and SMC studies, because we don't have such large studies carried out at the at such low or sub-SMC metallicities. Even in the case of Magellanic Clouds, you can see the winds are very weak compared to galactic counterparts. And in order to study such weaker winds, you basically need UV spectroscopy. Optical wind lines are typically in absorption, like in H-alpha, typically comes in absorption even for very early O dwarfs in both LMC and SMC. So one has to get to precisely get constraints on mass loss rates, one need to go for UV spectroscopy. In this figures, I tried to combine most of the UV spectroscopic analysis of massive stars, which try to derive the mass loss rate using UV analysis, and try to put them in log L versus log mass loss rate plot. So the right one is for SMC stars and the left one is for LMC stars. And this also includes some of the recent results from the X2-Ulysses collaboration. And of course, we would expect mass loss rate going down with the lower metallicities. So the metallicity, there's a metallicity scaling with mass loss rate. It's typically assumed as a power law, and the exponent can vary between 0.5 to 1.4, typically for OB stars. And it has been found from different theoretical predictions as well as from empirical studies. But again, all these constraints are just based on Milky Way, LMC, and SMC, just 3 different metallicities. We don't know what really happens when we go down to further sub-SMC or like very low metallicities. But even in SMC, one can clearly see there is a very noticeable trend with the mass loss rates. So most of the OB stars, especially OB dwarfs, has extremely weak wind or very low mass loss rate. Sometimes you can only get an upper limit on the mass loss rate because the UV wind line doesn't show any wind features anymore. They look more like a photospheric line. So compared to typical theoretical predictions from Wing or Bjorklund 2021, we can see that these OB dwarfs have extremely low mass loss rate. But again, we don't know what will happen at even sub-SMC or like even lower metallicities. There are only very few studies which try to derive or constrain wind parameters at very low metallicity. One of them was the recent work by Grace Telford, and she tried to analyze 3 stars, one from Liope, which has around 3% solar metallicity, and Sextans A star, and 1 star from WLM galaxy. So here she tried to constrain it with varying different mass loss rates and time velocities, and concluded that the stars in very low metallicity galaxies have extremely small terminal velocities or extremely low terminal velocities than one would expect from trans-extrapolating SMC, LMC, and galactic scaling. On the other hand, mass loss rate shows a very different trend. So here she plotted the mass loss rate from these 3 stars, comparing with Bjorklund predictions in the solid line and wind predictions in this 3 different points. And you can see these 3 stars in good agreement with the Bjorklund predictions for the corresponding low metallicities. we also try to get a constraint on the wind parameters of massive stars in the Magellanic Bridge, and especially one of the star found to have extremely low iron abundance, such as 3.6%. So for this star, ELISA tried to derive a preliminary mass loss rate and terminal velocities, try to see where this star will place on this diagram. And interestingly, the bridge metal poor star also has a similar property as shown by other two stars in these dwarf galaxies. So the velocities are extremely low, and the wind mass loss rate is also in agreement with the Bjorklund prediction. So when we compare it with what we observe from SMCOB stars, especially SMCOB dwarfs, what it looks like. So here I'm showing the same plot from these mass loss rates of these metal poor stars, comparing with mass loss rates of SMCOB stars. And here you can see that there is no big difference between SMC and sub-SMC stars. I mean, of course, the sample size is very limited at low metallicity, but at least with this limited sample, we don't see any strong reduction in mass loss rate compared to SMC. On the other hand, there is a very strong trend for reduction in wind velocities. So that means the wind properties can be very different at sub-SMC metallicities, and one cannot naively extrapolate these constraints to very low, so it has to be really cautious. And of course, this motivates us for more observations at sub-SMC metallicities and a detailed wind analysis to derive the parameters. This also motivate us to find new wind diagnostic lines, because in the UV, we are limited to a certain mass loss rate. So beyond 10 to the power minus 10 solar mass per year, if we are going to that extreme of low mass loss rate, we cannot anymore derive precise constraints on the wind mass loss rate just using the UV. So one has to look for other useful diagnostics lines, such as bracket alpha in the near infrared or even mid infrared. So here, showing one of the recent result from JWST media observations of a dwarf in the galaxy, which observed to have a very low mass loss rates from the UV and optical spectra, but then found to have a much higher mass loss rate in the just from the mid-infrared observations. So in order to really understand if these stars at low metallicity have a weak wind or not, we basically need further diagnostic lines. Okay, now I move on to another important parameters of OB stars, which is the ionizing photon feedback. So massive stars produce strong ionizing photons, and especially at metallicity is very important to understand how their feedback affects the environment. And in this plot, I am trying to show you how the spectral type versus number of hydrogen ionizing photons relation changes with different metallicity. So all the background red and blue lines are from points are from the LMC and SMC studies. And then comparing it with the very low metallicity stars from the Bridge and Sextans A and Liope. So you can see there is no really a clear trend for increasing number of ionizing photons when you go down to low metallicity. Of course, the sample size is low, and there is also a lot of scatter in spectral type versus low Q plot. But again, this doesn't show any completely different trend at low metallicities. With that, I will come to the last part of the talk, which is about binaries. And of course, binaries are extremely important for massive stars because at least 70% of them are expected to be in binaries, and at some point they're expected to interact. And especially in the context of low metallicity massive stars, it's very important to understand their evolution because they are expected to be the progenitors of this merging black holes or neutron star, which creates these gravitational wave observations. And here I'm showing a neutron star plus neutron star merging channel from the evolution of two ZAH main sequence massive stars. And I'm especially focusing on one of the very important stage, which consists of a strip star and a BE star. So understanding this stage was really puzzling for a long time because theoretical models predicts this stage, but we don't see much observation for this hot strip stars plus BE stars in our observation. So one would expect the strip stars to be in an intermediate mass range between subdwarf and Wolf-Rayet star, and especially at low metallicity, this range of mass extends for stripped helium stars because at low metallicity, Wolf-Rayet phenomenon only happens at much higher masses. And there are several predictions of evolutionary models suggesting that low metallicity indeed favors partial envelope stripping. So instead of fully stripping to a very compact helium star, we might also see a partially stripped star, especially at low metallicity. And these kind of objects will hide among OB stars because of the partial strip. And we still don't know if this is a long transition phase or a stable helium burning phase instead of a fully contracted strip star. So it will be very interesting to detect and characterize such objects at low metallicity. And here I'm showing a HR diagram with a zoo of strip stars basically. And on the higher mass end, you can see a population of Wolf-Rayet stars. And in the lower mass end, you can see a population of subdwarfs. And the intermediate mass range is more interesting because we didn't have much observations until recently. So recently, a few hot intermediate mass strip stars has been observed. And also at the same time, we also observed partially stripped stars in the same mass range. So we used multi-wavelength and multi-epoch spectroscopic analysis to characterize these intermediate mass partially stripped stars. And I will show you some of the interesting results from this study. For example, we found these stars are overluminous for their current masses and perfectly aligned with the core helium burning objects. And the secondaries, on the other hand, found to have very high masses than their corresponding stripped primaries. So they have mass ratios of more than 2. And the chemical composition is also very distinct compared to typical OB stars. And they found have strong nitrogen enrichment, carbon, and at the same time, carbon and oxygen is highly depleted. So you can see in this N2C to N2O diagram, they are completely separated from the typical, where we expect typical OB stars to be located, suggesting that there's a significant fraction of the layers are stripped during the binary interaction. And of course, it's very important to constrain the mass loss rates of these partially stripped stars to understand whether they have very strong mass loss rate like Wolf-Rayet stars, or if they have a very weak mass loss rate as OB stars. Actually, they have a mass loss rate kind of in between OB and Wolf-Rayet phases. And it's actually in good agreement with the Wing 2017 predictions. And again, especially related to the low metallicity, for example, SMC, OB stars have extremely low mass loss rate, but these partially stripped stars have comparatively much higher mass loss rate than the typical OB stars, which is also interesting in the context of low metallicity. Coming to their binary, how they evolve and how these objects are formed and evolve into how their future evolution would be. We try to understand it through creating MESA models and comparing it with observations. So in all these objects, they most likely had a case B mass transfer scenario, and all the evolutionary models suggest that the primaries probably have an initial mass in the range of 12 to 17 solar masses, and they have current mass around 3 to 8 solar masses, suggesting that these are firmly in the mass range to form a neutron star after a supernova explosion. And probably this will be progenitors of a stripped envelope supernova, followed by evolving to a B X-ray binary. And one interesting question here is whether this partially stripped stage is a very fast transition stage or more a very long stage of helium burning. So because this will affect how this will impact on the ionizing feedback, because if they are in the very hot strip stage, this will provide a lot of helium ionizing photon flux compared to if they are in a very cool phase. So this gives a summary of the talk. So so far we have quite good understanding of metal poor massive stars till 20% solar metallicity. Basically, SMC is the current anchoring point, but we still have following or current ongoing studies to understand sub-SMC metallicity stars at low metallicity dwarf galaxies or in the bridge. So bridge is actually a very unique laboratory in the which offers a very nearby or very close distance and a variety of metal poor stars starting from 50% to 3% solar, and it also offers stars with very distinct iron to alpha ratios. So it's a very rich sample to study metal poor stars in the very nearby distances. And we also see quite a different wind behavior at sub-SMC metallicities, but we need more observations and more detailed analysis to have better conclusions and constraints. And the same for binary evolution. We are currently discovering more post-interaction binary products at low metallicity, and this will be a very interesting objects to basically constrain the evolution of low metallicity massive stars towards forming compact object mergers. Thank you very much for listening.
Thank you very much, Varsha, for this very broad overview of many things you can do with metal poor stars, and also very interesting to see how this fits in a broader context. So time for questions. Do we have anyone who wants to comment or have a question? Miriam? Yeah, Miriam, can you?
Oh, I just made such a beautiful question that everybody missed. Hi, Varsha, sorry. I was wondering if you guys had explored any kind of explanation for the slowly rotating stars in the Magellanic Bridge.
Yeah, it's actually very puzzling. So mostly we see very fast rotating stars at low metallicity, as I showed in this distributional plots. But we don't have any conclusive ideas why these stars have such extremely low. It's not even just low, it's almost like close to zero. It's actually very puzzling. We had this ideas like probably some binary evolution or something might have happened before. But we don't have any conclusive ideas why these stars have such slow rotation. Yeah, but it's interesting at the same time.
Well, everything about this star is puzzling. Also,
Yeah.
the very different abundance patterns, even though they are nearby. Yeah. Well, thank you.
Nali, please.
Just responding to that discussion, and thank you, Varsha, lovely talk. Could it be that those stars with the very low rotation are simply seen pole on, and therefore you wouldn't see any line broadening? And it makes me wonder whether that means there's different abundance patterns that could result from that due to the view of them being pole on, and therefore if they really are rotating pretty fast, then you'd be seeing a different pattern through the atmospheres due to the oblateness of the stars. And a separate thing, I wanted to draw attention also to just looking at statistics for the binaries and the binary OBE stars. We were aware of that there's something like 3 or 4 OBE plus O star binaries in the SMC. And those can be compared to binary population synthesis models for the scenario that you proposed. And Irene Vargas Salazar, who recently defended her PhD thesis, has basically been doing that kind of thing. So I just wanted to mention that.
Thank you. So the pole-on scenario, yeah, technically there is a small possibility, but it's very unlikely that these two stars close by both have this pole-on. I mean, I'm not really sure, like maybe, but yeah. It's also one of the possibility, but it's very unlikely as well.
Could it be also that these stars are binary products? Because you were mentioning that these partially step stars, they are supposed to have
but then one would see such signatures in the surface abundance, for example, strong nitrogen enhancement and oxygen depletion, and so, but we don't see that. It looks like a normal main sequence star. There is no reason to think that it could be already interacted product.
Okay, Paco.
Hi, can you hear me?
Yeah.
Okay. Hi, Varsha. Really nice and complete talk. I think I was wondering these estimates of your terminal velocities and mass loss rates. I mean, especially at terminal velocities, but also the mass loss rates. How much are the terminal velocities upper limits, and then the mass loss rates, because you are using the carbon four line, and the mass loss rates and the terminal velocities, if you can show the profiles. Yeah, if you have you look at the nitrogen 5 line, and because things like, at least for these stars, things like a clamping or X-rays can really change a lot. I mean, you put a little bit more of X-rays, and then your star with 10 to the 9 to the minus 9 will go into almost pure absorption. And so I was wondering if you could use also, I mean, in the past, I think even for Taurus Co, which is, we know is quite a peculiar star, you look at the UV and you see very little things, so you have to go to the oxygen 6 line, which all of a sudden had a much higher terminal velocity. So I was wondering how much is that affected?
So unfortunately, we don't have oxygen 6. The spectra doesn't cover that range, but we have nitrogen 5. So we also will check, but because it's just a very preliminary result. It's not we have to carry out a very detailed analysis soon.
Yeah, I mean, I think it's very important that you account for X-rays and clamping.
Yeah,
if you put clamping, your carbon-4 line will get much stronger with a lower massless rate, and the opposite on the X-rays. So normally it's nice because you can combine differently. I mean, they react differently, the nitrogen 5 and the carbon-4 to these things. And then I have another question. You were talking about the different. I mean, it's really fine, really nice to see that you have completely different alpha to iron ratios. And I was wondering, you were using, I mean, how robust are those things? And you had an estimate of the silicon abundance as well. How much does it, or how much does the oxygen abundance go with the silicon abundance, which is also an alpha element?
So possibly, actually, when you look at the absolute number, especially for like silicon or magnesium, both stars have a very similar abundances, but it's just when you put it into the alpha to iron, because one star has extremely low iron, it makes this no difference.
Okay, so it's basically more the iron, not the alphas.
Yeah, exactly.
Okay.
Yeah.
Okay, thanks. Really nice stuff.
Anyone else want to ask Varsha or comment something? Yeah, now, please.
Hi, thank you for your talk. I'm interested in the metallicity of Magellanic Bridge, stars in Magellanic Bridge.
I'm sorry, I couldn't
Okay.
get you.
Thank you for your talk.
Yeah, please. What was the question?
Can you hear me?
Yeah, I can hear you.
Okay. Sorry. I'm interested in the metallicity of stars in Magellanic Bridge. Can we have a comment on the distribution?
Yeah, so exactly. So it's not like one particular metallicity we can associate in bridge stars. It's more complex than that. So even when you just consider the measured abundance of 3 different O stars, these have like completely different abundances, not just iron, but all chemical abundances are scaled very differently with each other. And when you also compare it with the literature values of abundance values of B stars and those measured from the ionized gas, this all gives like a very large distribution basically for each element. So there's it's very scattered between 50% and 3% metallicity.
Do you have the information about the abundance of gas?
This is basically from 2 studies from Lehner et al. 2008 and 2001. So they basically used UV spectroscopy of 2 stars, but then tried to get the line of sight diasom abundances.
Thank you.
Now I have 2 questions for my own curiosity. It's about how you find OV-star candidates to be observed in the Magellanic Bridge. So are there specific photometric surveys? And then what is the present situation and your perspectives in terms of increasing the sample further? Are you already kind of, you have everything can be useful, or you have plans to increase the sample?
Yeah, so the first question was referring to the O stars we discussed here. So these were, I would say, purely accidental. So there were like hundreds of spectra available for this region taken, I don't know, early 2000s. And yeah, I was basically going to search if there are like some interesting stars in this region, because previously people just thought there's only like a couple of B stars and then probably even low mass stars sitting there. But then we found these interesting O stars suddenly, and also found out that these also have like extremely iron poor. So we also carried out a follow-up spectroscopy of OB stars across the bridge, so that we can have like a systematic understanding of how the abundances varies in this whole region, because it's a very large region. We tried to cover it with we took basically a spectra of around 20 stars with the VLT UVS, and then also followed up it with the UV spectra, which is actually ongoing. So we'll get more data soon, and Elisa will carry out a detailed analysis with these observations.
Okay, so we'll hear from Elisa
Yeah.
in the next months, years or so. Okay, so is there any maybe last question? If not, Varsha, thank you very much again for accepting our invitation. It has been very, very interesting talk. And yeah, so thank you everybody for connecting also and participating in this initiative, and hope to see you in 1 month. Ciao, everybody.
Right.